Welcome back to another explainer. Today, we're taking a wild journey deep underground and eventually right into the jeweler's display case. We're going to unpack the whole shebang when it comes to gemstones, from the intense geological pressures that forge them in the dark to the cutting-edge science that actually defines them today. So get ready, because this is your complete, definitive explainer on the science, history, and art of gemstones.
Now, you might be wondering why this topic is just so captivating. Well, just consider this number for a second. As of 2023, the global industry valuation for colored gemstones, and by that we mean literally everything other than diamonds, sits at a staggering $1.55 billion US. And honestly, it doesn't stop there. Experts are projecting that figure to climb to $4.46 billion by 2033. That absolutely blows my mind, but it perfectly highlights our enduring global obsession with these tiny, shiny pieces of the earth. But what exactly are we spending all that money on?
Okay, let's dive into this. Here is our roadmap for today's explainer. We're going to start by defining the gemstone, then we'll look at how they're forged in the earth. After that, it's all about chemistry, color, and classification. Then we'll shift gears to the art of the cut, and finally, we'll wrap up with modern treatments and synthetic gems.
So, starting with part 1, defining the gemstone. Before a stone actually ends up sparkling in a ring or a necklace, what exactly makes a random rock worthy of that title?
When we hear the word gemstone, I bet most of us immediately picture hard, inorganic mineral crystals, right? Things like diamonds or sapphires. But the official definition is actually wonderfully broad. It's any piece of mineral crystal, certain rocks like lapis lazuli or opal, and even, get this, organic materials derived from living organisms, chosen for their beauty, durability, and rarity, then cut and polished for adornment. That means ancient hardened tree resin, like amber, or pearls formed inside oysters, are all officially recognized as gemstones. How cool is that?
Now, we definitely need to talk about this fascinating distinction between precious and semi-precious stones. You've heard these terms a million times. The traditional Western classification puts diamonds, rubies, emeralds, and sapphires on a pedestal as the elite precious stones, basically tossing everything else into the semi-precious bucket. But we really need to dismantle this myth right now. Precious does not strictly mean more valuable. Today, it's honestly just a historical marketing term. To put it in perspective, a rare, vibrant green, semi-precious tsavorite garnet can easily outprice a mid-quality precious emerald. It's all about rarity and desirability, not just some ancient label.
That being said, though, the historical gravitas of those traditional precious stones is absolutely undeniable. Since the dawn of civilization, ancient cultures revered them. Take the ruby. In ancient Sanskrit, the ruby was called Ratnaraj, which translates to the king of precious stones. I mean, what a title, right? These weren't just pretty rocks to them. They were literal symbols of ultimate power, wealth, and mysticism.
Moving on to part 2, forged in the earth. We're looking at geological formation now. How does the earth actually go about creating a Ratnaraj, a king of precious stones? Let's look at the majestic, deep earth processes that forge these marvels.
So, the vast majority of gemstones are formed anywhere from 3 to 25 miles deep within the Earth's crust, though a rare few, like diamonds, are born even deeper down in the mantle. They're created under just unimaginable extremes of heat and pressure. And here's where we really need to pause for a second and appreciate the sheer scale of time involved. This is not a quick process. We're talking about millennia here, thousands, if not millions of years of minerals just slowly cooking in the crust across igneous, metamorphic, and sedimentary rocks. It's mind-boggling.
Because of those incredibly diverse and intense underground pressures, gems come out with vastly different physical properties, especially when it comes to durability. So how do we measure that? Enter the Mohs scale, which was introduced way back in 1822. It rates a mineral scratch resistance from 1 to 10. A stone like talc is a 1. It's so soft it would literally crumble in jewelry. Quartz sits at a 7, which is decent for occasional wear. But when you get up to a 9, like corundum, which includes rubies and sapphires, or a perfect 10, like diamond, you've got ultimate durability. This is exactly why an engagement ring is usually a diamond or sapphire, and for sure not a soft or fragile mineral that belongs safely behind museum glass.
All right, part 3, chemistry, color, and classification. We're identifying gemstones now. We've got our tough, crystallized mineral pulled from the dirt, so let's explore its atomic identity.
Consider this little riddle for a moment. Why is a ruby famously red, but a sapphire famously blue? To the naked eye, they look like completely different stones from completely different families, right?
Well, the secret actually lies in atomic impurities. Prepare to have your mind blown. Rubies and sapphires are actually the exact same base mineral, corundum. Pure corundum is just colorless aluminum oxide. But deep underground, these microscopic trace impurities sneak into the crystal structure. Think of these impurities exactly like spices in a cooking recipe. If the earth adds a pinch of chromium to the corundum, bam, it turns a vibrant red and we call it a ruby. But if the earth adds iron and titanium instead, it turns a deep blue and we call it a sapphire. Literally the same rock, just different spices.
Of course, sometimes a bit more than just atomic spices get trapped inside. As these crystals grow over millions of years, they often swallow up little bits of other minerals, gas bubbles, or even fluids. We call these inclusions. Now, you might initially think of these as flaws that ruin a stone, but actually, to a gemologist, these inclusions are highly valuable geological fingerprints. Under a microscope, an inclusion can tell an expert exactly which country or even which specific mine a stone was formed in. And most importantly, it proves the stone is of natural origin.
Let's jump to part 4, the art of the cut, where we unlock that brilliance. Nature has done its part over millions of years, right? So now it's our turn to shift to the meticulous human craftsmanship of the lapidary or the gem cutter.
Believe it or not, most gemstones just look like boring pebbles in their rough state. To unlock their true beauty, they have to be cut. For thousands of years, the only way to do this was the cabochon cut, which is essentially grinding the stone into a smooth, rounded, polished dome. It's gorgeous, but it relies purely on the stone's surface color. It actually wasn't until around the 14th century that human technology allowed for the faceted cut. This is where a cutter creates tiny, mathematically precise flat windows, or facets, at exact angles. If those angles are perfectly calculated, light enters the stone, bounces around the inside like a pinball, and blasts back out to your eye, creating that dazzling, blinding sparkle we're all so obsessed with today.
Once a stone is beautifully cut, we have to measure its value, and as you probably know, we do that using carats. But there is a huge, very common misconception here. People almost always think carat means the physical, visual size of the gem. It doesn't. Carat is strictly a unit of weight. Exactly 5 carats equals 1 gram. And because different minerals have totally different densities, a highly dense 1 carat ruby is actually going to look visibly smaller on a ring than a less dense 1 carat emerald. So remember, weight does absolutely not equal visual size across different gem species.
All right, heading into our final stretch, part 5, treatments and synthetic gems. We're entering the fast-paced, high-tech, modern era of gemology, so let's talk about human intervention. So for centuries, humans haven't just cut stones. We've actively treated them to make them look better. And today, the vast majority of gems on the market undergoes some form of treatment. Heat treatment, for instance, is incredibly common for sapphires and rubies to permanently enhance their color and melt away internal cloudiness. For emeralds, which naturally have a lot of cracks, oil or wax is forced into the stone to disguise those fissures. Some larger, highly fractured rubies are quite literally injected with molten lead glass to hold them together and improve clarity. And organic gems, like pearls or jade, they're routinely bleached to achieve that perfect color.
But today, we don't just treat natural stones anymore. We can literally build our own from scratch. And here is where we really need to clearly differentiate between a cheap imitation and a true synthetic gemstone. An imitation is just cubic zirconia, glass, or plastic. It's a fake that just happens to look like a gem. But a synthetic, lab-grown gemstone? That is a real gemstone. It is chemically, physically, and optically identical to the stone pulled from the dirt. It has the exact same crystal structure, the exact same hardness, the exact same refractive index, the whole 9 yards.
And the process of actually building these is straight out of science fiction. The most cost-effective method is called the Vernal flame fusion process. We literally take powdered chemicals, like aluminum oxide for a ruby, and drop them through a 2000 degrees Celsius oxyhydrogen flame. The powder melts instantly, drops onto a spinning ceramic pedestal, and solidifies layer by microscopic layer into a flawless crystal tower called a boule. In just a matter of hours, humans can completely replicate the identical chemical magic that takes the Earth millions of years to pull off.
Which leaves us with a truly fascinating final thought for this explainer. If a lab-created ruby is optically flawless, structurally identical down to the atomic level, and visually more perfect than almost anything pulled from a mine, where does its true value really lie? Is it the millions of years of chaotic underground history that makes a stone precious? Or is it the sheer aesthetic perfection we can now engineer in an afternoon in a lab? It's a massive question that is currently reshaping the entire multi-billion-dollar jewelry industry.
Thank you so much for joining me today. I hope you never look at a piece of jewelry the exact same way again. Keep exploring, and I'll catch you in the next one.